I want to start with talking about, imagine if we can connect people with internet via lasers. And my capstone really wants to show ideas and work that can build towards solving these problems and solving things around this goal. And I will give a little bit of an introduction to kind of free space optical links. A little bit about free space optical links is that we can communicate data through lasers by pulsing them very quickly. This satellite, most people think about this in the applications of satellites, and satellites can need to be able to send data to each other and back to ground potentially. There's a lot of companies that are working on this project. However, there might also be an application for optical links to be used where fiber cannot be placed. And so this could be used on terrestrial ground-to-ground communications. For example, in places where fiber is difficult to put down, difficult terrains, rivers, train tracks, highways, and other city-to-rural possibilities would be a use for these optical links. And the space in which optical links have been developed, there are capabilities with these lasers to communicate data. But the challenges I want to be working on are the supporting problems. And this is about kind of the challenges of initially aligning those lasers, keeping those lasers tracked, and communicating to the systems before the lasers are aligned. Because oftentimes these are done in places where there is no communication channel. So to get started with this problem, I needed to first make a system that could shoot a laser and shoot a laser with relative consistency and accuracy. Therefore, made a quick prototype of a laser system that can move in both tip and tilt. This allows for the laser to be moved in the way the drawing indicates. That, combined with a simple circuit of 2 stepper motors and an argon, while the laser's on a separate power supply. Here on the left, you can see the circuit and the 3D printed, integrated together. In the middle, you can see the front side of that and the laser being on. And then on the right was the controller I programmed. This is connected via Bluetooth and the Bluefruit app. And so each, the arrows, they move the laser, as you could guess. 1 and 2 increase the amount I'm moving and decreasing the laser movement. And there's 2,048 steps per rotation of these stepper motors. So I can get a relatively fine movement for a desktop setup, but not necessarily for the application of what that is. And there are ways to scale that. And then buttons 3 and 4, I'll talk about a little bit later. I'm not. Sorry, just making sure my video is not playing immediately for some reason. I cannot play this media for some reason, so I'm gonna move on to the next slide, but you would see this in motion via the Bluetooth app. And so first, it was kind of developing 3 of the kind of scanning patterns. The red dot represents the laser, and then these paths represent what I was trying to follow. The first system was the horizontal scan. This is to find where the laser is in space. And this is to create a scan a large amount of area. And in real life, this would be stretched more horizontally and less vertically. And the code does allow for that manipulation to be done easily. And I believe this video is playing, so that's great. So this is showing you the kind of horizontal scan, and that's what 3 and 4 on my Bluetooth controller did, was activate these scans. And a lot of the coding challenges with the 2 systems was less about how to make the lasers move, but how to execute code in a way that allows other functions to happen between steps. And so this is kind of an example of a blocking function that the stepper motor creates, and my logic to work through steps so that I'm able to execute other codes and things. And a lot of the challenges I faced were about realizing differences between the operations that happen in milliseconds, microseconds, and that translation into real life. The second type of scan was a spiral scan. It was initially developed as a way of, like, if you were close to the target to a relatively known point, and you would scan outwards from it. You can see this going, and it's slower in the middle, and then it speeds up as it goes outside to keep a consistent rate of movement. The third scan, the parabola scan, this was made because for the application of these devices would potentially be on a pole, and they would be swaying back and forth, and so we would know that the way that these devices would move would be similar to a parabola on a flexing pole. So developing a method for a scan to work in that way was important. But in reality, the horizontal scan is really the main focus of this capstone project, because it'll show you kind of initial alignment. So next step, once I had some scans working, was to create a detector side. This is a simple photodiode measuring the amount of light that is hitting it. However, the challenge here was to create a feedback loop where I could take the data from the photodiode and translate it to useful information for the other side. Here's a quick little fritzing of that. As you can see, we have two separate systems, and currently it is a wired connection. This was mainly done so I could do testing of the algorithms quickly. And so this video should play. Perfect, okay. So whenever the photodiode received a higher value, it would record that and send a signal back to the other side to tell it where it was in position. And then it would snap back to the position where it was supposed to land. And so this was kind of a big like success point in this setup. However, it is a wired connection, and since it is a wired connection, I wouldn't be able to actually use this in a real system. It would defeat the point of an optical system. So next step was to create a different method for creating this feedback loop. And so a LoRa module was used. LoRa is a long-range, low-power radio frequency communication method. Its range is up to 10 kilometers without obstruction, or in the case of line of sight, we can get up to 10 kilometers. And so what that did was give me the ability to separate the systems and no longer have a physical connection between the two, which is key. And there is a bit of a time difference between the two LoRa's, and that 2.1 seconds to send and receive was measured from sending an initial signal, measuring the time it took to get the signal from the other side and receive that signal back. So in reality, it's a 1.1 or 1 second delay. And when we're talking about 1 second delays, it's actually a big difference when we're in time, when we're executing commands in microseconds. So we will be missing the laser by quite a bit. And so a calibration method had to be made where I would start the timer on one side. Hope this video plays. Would start the timer on one side, send a signal, calibrate it with that delay, and then have it come back and retrack the position from two timers on different sides. And this video shows us shooting it from halfway across the room for the kind of size of the laser, and allowing the photodiode to be detected. And so some kind of future implementations. I was working on this little prototype here, and it was for the ability to scan across multiple photodiodes and to be accurately center between the diamond pattern of the detectors. And if the beam drifted towards a direction, we would be able to recorrect based on that. So the next step is including multiple photodiodes into the same system and to give you more feedback and data. So then the kind of receiver side after that was 3D printed, and I mounted it to one of the lamp poles and holders in the classroom. You can see a little bit more close up here, and then I can show you the video of this working in a isolated area in space. And so basically, if I have a link, I know I could transfer. If I'm pointed in the right area, I know I would be able to transfer data to that spot. And just to kind of end, I hope the capstone project showed some development in the supporting tech around the communication devices. I want to thank you for your time for listening. Our boot camp instructors, peers, and also people supporting the program in the background. And I'd like to open up to questions now.